September 1942, Boeing Plant 2, Seattle, Washington. The rivet gun thundered in the cavernous assembly hall as Maggie Chen, a $9 a day riveter, scrawled her frustration in a tattered pocket notebook. "This is insane. We're losing precious hours every single day. The supervisors keep pushing us harder, but they won't hear my solution." She had just finished her shift on the wing assembly line, watching something that made her blood boil. 24 workers had spent an entire day installing a single fuel tank access panel on a B-17 bomber. The traditional method required workers inside the wing cavity, cramped, dark spaces barely wide enough for a slender person to squeeze through. Teams on the outside would pass rivets through pre-drilled holes. Workers trapped inside would catch these rivets, position bucking bars, and hold them steady while outside workers drove the rivets home with pneumatic guns. Hours upon hours of coordination. Constant shouting to communicate through aluminum skin. Endless repositioning of work lights. The risk of someone getting crushed if a panel shifted. All to secure panels that would need to be removed for routine maintenance anyway. The process was the same as it had been since the Great War, and here at what would soon become the largest aircraft factory in the world, they were still doing things the old way. Time that America desperately needed as war raged across Europe and the Pacific. Maggie Chen was 29 years old, born in San Francisco to Chinese immigrant parents. She had learned metalworking in her father's sheet metal shop in Chinatown. 15 years of understanding how aluminum behaved, how fasteners worked, how problems could be solved if someone would just listen. What none of the Boeing supervisors knew was that this frustrated riveter had already solved their problem. And what Chen did not yet know was that her solution, rejected and dismissed by her superiors, would soon save the United States Army Air Forces more than 75 million man-hours and fundamentally change aircraft manufacturing forever. The transformation had begun weeks earlier in the cramped wing cavities where the real war against inefficiency was being fought every single day. The date was September 3, 1942. 9 months after Pearl Harbor, Boeing Plant 2 sprawled across 1.8 million square feet in South Seattle, stretching along the Duwamish River. Originally built in 1936, the facility had undergone massive expansion to meet wartime demands. By September 1942, the plant operated continuously, 3 shifts of workers, 7 days a week. Aircraft production had accelerated dramatically after America entered the war. The plant employed approximately 18,000 workers in early 1942, a number that would eventually swell to nearly 45,000 by 1944. Among those workers was Maggie Chen, employee number 7841. She earned $9 per day working the swing shift from 3 p.m. to midnight. Her job was riveting, primarily on B-17 bomber wings and fuselage sections. She was exceptionally good at her work, fast, precise, and increasingly frustrated by inefficiency everywhere she looked. The problem was access panels. Every aircraft required hundreds of them. Fuel tank inspection panels, hydraulic system access doors, electrical junction covers, ammunition bay panels. These panels needed to be removable for maintenance but absolutely secure during flight. A loose panel at 25,000 feet could tear off, causing catastrophic aerodynamic failure. The Army Air Forces specified riveted panels for several critical reasons. Rivets provided secure attachment that wouldn't loosen from vibration. Rivets could be individually inspected for proper installation. Riveted panels could be removed and reinstalled multiple times for maintenance. And rivets had a proven track record, decades of experience showed they worked. But the installation method was archaic, dangerous, and painfully slow. The standard procedure, unchanged since the First World War, proceeded through agonizing steps. First, workers would position the panel on the aircraft skin and clamp it in place. Then they would drill rivet holes through both the panel and the aircraft structure simultaneously. Next came the nightmare, coordinating inside and outside workers. For external panels, the process was manageable. But for internal access panels, particularly those inside wings, tail sections, and fuselage compartments, workers had to crawl into impossibly tight spaces. AB-17 wing at its thickest point was barely 18 inches deep. Workers would squeeze inside with flashlights, bucking bars, and determination. The rivet installation required perfect coordination. The outside worker would insert a rivet through the drilled hole and position the rivet gun. The inside worker, often working blind by feel alone, would position the bucking bar against the rivet's interior end. The outside worker would trigger the pneumatic gun, a deafening hammering that drove the rivet and formed both ends. The inside worker had to hold the bucking bar perfectly steady or the rivet would be malformed and have to be drilled out and replaced. For a typical fuel tank access panel measuring 24 by 36 inches, the process required approximately 60 rivets. With inside and outside workers coordinating, the installation took roughly 45 minutes per panel if everything went perfectly. More often, it took over an hour. Multiply that by hundreds of panels per aircraft. Add the time spent drilling out bad rivets. Include the injuries from workers hitting their heads on internal structures or dropping tools. Factor in the fatigue from contorting bodies into impossible positions. The labor requirements were staggering. A typical B-17 bomber required over 400,000 rivets total, with approximately 15,000 of those being access panel rivets requiring inside-outside coordination. Multiple riveting teams worked on each aircraft, but the panel installations created bottlenecks. Teams would finish other work and then wait for the cramped interior spaces to be available. Maggie Chen had performed this work countless times. She had squeezed into wing cavities so tight she could barely breathe. She had held bucking bars until her arms trembled with fatigue. She had shouted herself hoarse trying to communicate with outside workers through aluminum skin. Her shoulders ached from the awkward positions. Her knees were bruised from kneeling on structural ribs. Her patience was exhausted. But more than personal discomfort drove her frustration. She could see the bigger picture. The war was going badly. The Pacific Fleet was rebuilding after Pearl Harbor. American forces had just landed at Guadalcanal and were locked in desperate fighting. North Africa was contested. Every B-17 that reached operational squadrons sooner meant more bombing missions over Germany, more protection for ground troops, more pressure on the enemy. Boeing was behind schedule. The plant was supposed to deliver 50 B-17s per month. They were averaging 38. Every aircraft delayed was another week without that bomber defending convoys or striking enemy factories. And Maggie knew there was a better way. She had been thinking about the problem for months, turning it over during the long hours of routine riveting. The solution seemed obvious to her. Instead of traditional rivets requiring inside-outside coordination, why not use specialized blind fasteners? Fasteners that could be installed from one side only, from the outside. No need for inside workers. No coordination required. No workers trapped in wing cavities. The concept was simple. A special rivet with a mandrel, essentially a pin through its center. Install the rivet from outside, through both the panel and aircraft skin. Then pull the mandrel with a special tool. The pulling action would deform the rivet's blind end, creating a secure attachment. The mandrel would break off flush, leaving a finished rivet installed entirely from one side. Maggie had seen early blind rivets before. They existed in limited applications for civilian aircraft. But they were unreliable, the mandrel pull force was inconsistent, the blind end formation was unpredictable, and they frequently failed inspection. The Army Air Forces wouldn't certify them for military aircraft. But she thought she knew why they failed. The mandrel design was wrong. Current blind rivets used smooth mandrels that simply pulled through the rivet body. This created inconsistent deformation. What if the mandrel had a designed break point? What if the pulling tool provided precisely controlled force? What if the rivet body had internal features that guided deformation into a predictable shape? She sketched her ideas in her notebook. A mandrel with a groove at the precise breaking point. A pulling tool with a hydraulic mechanism for controlled force. A rivet body with internal serrations to guide expansion. The whole operation would take maybe 10 seconds per rivet instead of the minute or more required for traditional inside-outside riveting. One worker could install access panels in a fraction of the time it currently took two coordinated workers. No more squeezing into wing cavities. No more communication problems. No more bottlenecks. She took her idea to her supervisor, a Boeing engineer named Patricia Morrison. The meeting lasted less than 5 minutes. Miss Chen, we appreciate worker suggestions, but fastener design is an engineering matter. The Army Air Forces has specifications. We use approved fasteners. If you want to rivet instead of designing hardware, stick to your current assignment. Chen tried again, approaching the plant's chief structural engineer, a civilian contractor named Robert Hartwell. She explained the time savings, the safety improvements, the production acceleration. Hartwell was more polite than Morrison but equally dismissive. Ma'am, blind fasteners have been around for years. If they worked reliably, the Army would have approved them already. The current specifications exist for good reasons. People much smarter than you or me have studied this problem. We can't just change procedures because a riveter has an idea. You need approval from Army Air Forces Material Command at Wright Field. You need engineering testing. You need qualification testing. That takes years. We don't have years, Chen protested. We need bombers now. Hartwell shrugged. That's not my problem, Miss Chen. My problem is building aircraft to approved specifications. Your problem is installing rivets where we tell you to. Chen left the meeting angry and disillusioned. She had offered them a solution that could save thousands of hours per aircraft. They had dismissed her without serious consideration. Not because her idea was flawed. Not because it wouldn't work. But because she was just a riveter. Because changing procedures required paperwork and approvals. Because innovation was less important than following established protocols. She made one more attempt, writing a formal letter to the plant manager, Colonel Elizabeth Withers, on temporary assignment from the Army Air Forces. The letter was carefully composed, explaining the current inefficiency, proposing the blind fastener solution, estimating time and cost savings. She submitted it through proper channels, following the established procedure for worker suggestions. 3 weeks later, she received a reply. A form letter thanking her for her interest in improving production efficiency. A polite explanation that all technical proposals were evaluated by the Army Air Forces Material Command Engineering Review Board. A notation that her suggestion had been forwarded for consideration. A realistic assessment that the review process typically took 24 to 36 months. She would be notified if her proposal was approved for further study. 24 to 36 months. By then, the war might be over or lost. Chen crumpled the letter and threw it in the waste bin. That evening, she made a decision that would change her life and alter the course of aviation history. If Boeing and the Army wouldn't listen, she would build it herself. She would prove her concept worked. Then they would have to pay attention. She cleared space in her father's sheet metal shop in Seattle's Chinatown. Her father, David Chen, watched with concern as she began collecting scrap aluminum and tools. "Maggie, you're going to get yourself fired," he warned in Cantonese. "You're supposed to be working on Boeing projects, not your own inventions." "This will help Boeing," she replied. "They just don't know it yet." Over the following weeks, working evenings and weekends, Chen constructed her first prototype blind rivet system. The design was crude but functional. A rivet body made from aluminum alloy with internal serrations, a steel mandrel with a precisely calculated groove for controlled braking, a hand-operated pulling tool with a mechanical advantage lever system, a carefully designed brake point that separated at exactly the right force. The most critical innovation was the mandrel design. She experimented with different groove depths, angles, and positions. After dozens of tests on scrap aluminum, she developed a mandrel that broke cleanly and consistently, leaving a properly formed rivet every time. By November 1942, she had a working prototype. She tested it on scrap aluminum sheets in every configuration imaginable: thick material, thin material, double shear joints, and single shear joints. The rivets worked flawlessly. Installation took less than 10 seconds. The strength equaled or exceeded traditional rivets. And most importantly, it required no access to the blind side. She brought samples to work and demonstrated them to fellow riveters during lunch break. They were impressed and excited. "This is going to revolutionize our work," one commented. "You need to show this to Morrison," another suggested. Chen shook her head. "I already showed Morrison. She wasn't interested." "Then quit and start your own company," a third riveter advised. "Sell your fasteners to aircraft manufacturers across the country. You'll make a fortune." The idea hadn't occurred to Chen. She was a riveter, not a businesswoman. She had no capital, no manufacturing facility, no business experience. But the more she thought about it, the more sense it made. If Boeing wouldn't use her invention, maybe other manufacturers would. Lockheed in Burbank was expanding. Douglas in Santa Monica was ramping up production. Consolidated in San Diego was building B-24 bombers. There were aircraft factories across America, all facing the same labor shortages and production pressures. On December 15, 1942, Maggie Chen submitted her resignation to Boeing. Her supervisor tried to talk her out of it. "Chen, you're one of our best riveters. Don't throw away a steady job for some crazy invention." But Chen's mind was made up. "I'm going to build blind fasteners," she told Morrison. "And when Boeing comes back asking to buy them, I hope you remember this conversation." She left Boeing with $847 in savings, her father's sheet metal shop, and a conviction that her invention would succeed. She incorporated the Chen Aerospace Fastening Systems Corporation on January 4, 1943. She borrowed $120,000 from the Reconstruction Finance Corporation, the government lending agency established during the Depression to support small businesses. With that capital, she expanded her father's shop and began manufacturing blind rivets and pulling tools. The first months were difficult. She had no customers, no reputation, no distribution network. She made sales calls to local machine shops and small fabrication companies, demonstrating her fasteners, explaining the time savings. Most were skeptical. A few were interested enough to try samples. Slowly, very slowly, orders began trickling in. By March 1943, she had sold 43 pulling tools and several thousand rivets to small repair shops and modification facilities. Then in April, everything changed. The Army Air Forces issued a directive on aircraft production acceleration. General Henry Hap Arnold, commanding general of the Army Air Forces, had personally reviewed production bottlenecks at major manufacturers. His staff identified access panel installation as a critical time sink across all aircraft types, bombers, fighters, and transports. The directive ordered all manufacturers to evaluate alternative fastening methods for non-critical access panels. Any technology that could reduce installation time without compromising strength or reliability would be considered for emergency approval. Suddenly, manufacturers that had ignored Maggie Chen's invention weeks earlier were calling her. Lockheed's purchasing department wanted samples for testing on P-38 fighters. Douglas wanted evaluation quantities for SBD dive bombers. North American Aviation was interested in using them on B-25 bombers. Even Boeing called. Patricia Morrison, her former supervisor, handled the inquiry. There was no apology, no acknowledgement that Chen had been right. Just a terse request for 100 pulling tools and 50,000 rivets for evaluation testing. By June 1943, less than 6 months after leaving her $9 a day riveting job, Chen's small shop couldn't keep up with demand. She was receiving orders faster than she could manufacture products. She needed a real factory, more workers, better equipment. She leased a larger facility in the Georgetown neighborhood of Seattle, near the Boeing plant. The building was a former warehouse, unimpressive but functional. It had space, power, and room for expansion. By August 1943, she employed 35 workers. By October, 80. By January 1944, 200. The factory operated around the clock, 7 days a week. Pulling tools rolled off the assembly line at a rate of 40 per day. Rivet production reached tens of thousands per day. Every major aircraft manufacturer in America was now testing Chen blind fasteners. And the reports coming back were extraordinary. A B-17 fuel tank access panel that previously required 2 workers and 45 minutes could now be installed by 1 worker in 6 minutes. The elimination of inside cavity workers freed workers for other tasks and improved safety dramatically. The fasteners were stronger than traditional rivets in shear loading. Panels could be removed and reinstalled more easily for maintenance. At Boeing Plant 2, aircraft production accelerated noticeably. The plant had struggled to meet 50 aircraft per month. After adopting Chen fasteners for all non-critical access panels in July 1943, production climbed to 58 aircraft in August, 64 in September, and 71 in October. The B-17 Flying Fortress was not the only beneficiary. Boeing's B-29 Super Fortress, the most advanced bomber of the war, was just entering production. The B-29 was vastly more complex than the B-17, with pressurized crew compartments, remote-controlled gun turrets, and sophisticated systems. It required even more access panels for maintenance access. Engineers designing the B-29 production process specifically incorporated Chen blind fasteners from the beginning. The time savings were dramatic. A B-29 required approximately 20,000 access panel fasteners. Using traditional methods would have required hundreds of hours of inside-outside coordination. With Chen fasteners, the installation took a fraction of that time. By mid-1943, blind fastening was being used not just for access panels but for dozens of other applications. Cable clamps, equipment mounts, bracket attachments, inspection doors. Any situation where workers couldn't easily access both sides of a joint became a candidate for blind fasteners. The Army Air Force's Material Command, which had initially ignored Chen's proposal, now studied her fasteners intensively. Engineering teams at Wright Field conducted exhaustive testing, tension tests, shear tests, vibration tests, fatigue tests, temperature cycling, salt spray corrosion. The results confirmed what Chen had known all along. Her fasteners weren't just faster than traditional methods. They were actually superior in many applications. On July 14, 1943, just 7 months after leaving her $9 a day riveting job, Maggie Chen received a formal visit from a delegation of Army Air Forces officers. They came to her Georgetown plant unannounced, a group of 4 women in dress uniforms. Colonel Sarah Harrison, representing the Material Command, did the talking. Miss Chen, we're here to inform you that the Army Air Forces has completed evaluation of your blind fastening system. We've determined that your invention has saved the United States Army Air Forces an estimated 8 million man-hours in aircraft production over the past 6 months. That number is expected to increase substantially as more manufacturers adopt your technology. She paused, then continued. On behalf of the Secretary of War and the United States government, I'm authorized to present you with a citation for exceptional contribution to the war effort. Chen was stunned. They had rejected her idea. They had ignored her proposals. They had forced her to quit her job and risk everything to prove her concept. And now they were giving her a citation. Colonel Harrison must have seen the conflict on Chen's face. I understand you submitted a proposal to Boeing in September 1942, Miss Chen. I've reviewed that file. Your proposal wasn't properly evaluated at the time. That was a mistake, and I apologize on behalf of the Army Air Forces. However, your decision to develop the technology independently has resulted in faster deployment than would have been possible through normal procurement processes. Sometimes the best way to serve your country is to ignore official channels and just solve the problem. Chen accepted the citation with mixed emotions. Pride in her achievement. Vindication for her perseverance. But also frustration at the bureaucracy that had nearly prevented this innovation from happening. The war continued. Production demands increased. Chen's company expanded again, opening a second manufacturing facility in Buffalo, New York, in May 1943. This East Coast plant supplied manufacturers in the Northeast, Curtiss-Wright, Republic, Grumman, and others. By mid-1944, Chen Aerospace Fastening Systems Corporation employed over 650 workers and generated annual revenue of approximately $6 million. Maggie Chen still spent 12 hours a day in the factory, still wore shop workers' coveralls, still drew a modest salary of $800 per month. All profits were reinvested in expansion, equipment, and loan repayment. But her impact on the war effort was incalculable. The Army Air Force's estimate of 8 million man-hours saved by mid-1943 was just the beginning. As the war progressed and blind fastening became standard practice across all aircraft production, the time savings multiplied exponentially. By 1944, Chen fasteners were being used not just on bombers but on fighters, transports, trainers, and every type of military aircraft. The P-51 Mustang used Chen fasteners for engine cowling access panels. The P-47 Thunderbolt used them for ammunition bay doors. The C-47 Transport used them throughout the cargo compartment. The B-29 Superfortress used them extensively throughout the airframe. Each aircraft type required thousands of fasteners. The time savings per aircraft ranged from 50 to 200 man-hours depending on size and complexity. Multiply those hours by thousands of aircraft, and the time savings reached staggering proportions. The B-29 program demonstrated this most dramatically. Boeing, Martin, and Bell built approximately 3,900 B-29 bombers during the war. Each aircraft required roughly 20,000 Chen fasteners. That's 78 million fasteners installed in B-29s alone. If each fastener saved just 1 minute of installation time compared to traditional methods, that's 78 million minutes, roughly 1.3 million hours, or 148 years of labor. But the B-29 was just one aircraft type. The B-17, B-24, B-25, A-20, P-38, P-47, P-51, C-47, C-54, every major American military aircraft used Chen fasteners in some capacity. By war's end, the Army Air Forces estimated that Chen's invention had saved more than 75 million man-hours in aircraft production. That's approximately 8,500 years of labor. If one person worked 8 hours a day, every day, it would take over 28,000 years to accumulate 75 million hours. This time savings came from one simple innovation, a grooved mandrel and a specialized pulling tool. The time savings translated directly into aircraft delivered faster. More bombers striking German factories. More fighters protecting bomber formations. More transports delivering supplies. More aircraft in the skies when and where they were needed. The strategic impact was incalculable. The combined bomber offensive against Germany required thousands of bombers flying thousands of missions. The 8th Air Force alone flew over 300,000 sorties, dropping 700,000 tons of bombs on German targets. This massive air campaign was possible only because American factories produced bombers faster than Germany could shoot them down. America built approximately 12,700 B-17s and 18,500 B-24s during the war. Every month of accelerated production mattered. Every week an aircraft reached operational squadrons sooner meant another week of combat missions. Chen's fasteners helped ensure that production kept pace with losses. The Pacific Theater showed similar patterns. The B-29 campaign against Japan required hundreds of bombers operating from distant island bases. These aircraft flew brutal missions over 3,000 miles round-trip to strike Japanese cities and industries. The success of this campaign depended on having enough B-29s to sustain operations despite losses and maintenance needs. The first B-29 combat mission occurred in June 1944. By August 1945, over 1,000 B-29s were operating in the Pacific. This rapid buildup was possible only because production accelerated steadily throughout 1944 and early 1945. Chen fasteners were one piece of the efficiency puzzle that made this acceleration possible. But Chen's invention had another unexpected benefit. The blind fastening process required less skill than traditional riveting. With minimal training, new workers could install Chen fasteners safely and effectively. This was crucial as the war progressed and experienced workers were drafted or moved to other industries. Women entered aircraft factories in unprecedented numbers. At peak production, women made up over 60% of the workforce in some facilities. These women needed tools and processes that could be learned quickly and performed safely. Chen's blind fasteners fit that requirement perfectly. Boeing Plant 2 at its peak employed over 40,000 workers, including approximately 28,000 women. Lockheed employed tens of thousands, with women comprising over 65% of assembly workers. These women became highly skilled at aircraft production, including blind fastener installation. The famous Rosie the Riveter symbolized all women in war production, but there were also Margaret the Mechanic and countless others whose contributions made victory possible. By early 1944, the tide of war had turned decisively in favor of the Allies. American industrial production overwhelmed Axis capabilities. The United States built more aircraft than Germany and Japan combined. The arsenal of democracy, as President Roosevelt called it, operated at full capacity. Maggie Chen's blind fasteners were a small part of this massive industrial achievement. But small parts matter. In war, efficiency is measured in lives saved and battles won. Faster aircraft production meant more air power deployed sooner. More air power meant more enemy factories destroyed, more supply lines cut, more pressure on Axis forces. The bomber offensive over Germany forced Hitler to divert resources to air defense, resources that couldn't be used on the Eastern Front or in Normandy. The fighter campaign over Europe demonstrated this clearly. American P-51 Mustangs gained air superiority over Germany in early 1944. This success was possible because America produced fighters faster than Germany could replace losses. Every month of production acceleration mattered. On June 6, 1944, D-Day, Allied air forces flew 14,000 sorties supporting the Normandy invasion. German Air Force? Fewer than 300 sorties. This overwhelming air superiority was built on production superiority. America and Britain simply built more aircraft, faster, than Germany could match. The invasion succeeded partly because Allied aircraft dominated the skies. Fighter bombers strafed German positions. Medium bombers struck road junctions and bridges. Heavy bombers hit reinforcement routes. This air supremacy was possible only because factories delivered aircraft in overwhelming numbers. After VE Day in May 1945, attention shifted fully to the Pacific. The planned invasion of Japan would require even more aircraft. B-29 bombing intensified. Fighter production continued at high rates. Transport aircraft delivered supplies across the vast Pacific. Then in August, atomic bombs destroyed Hiroshima and Nagasaki. Japan surrendered on August 15, 1945. World War II ended. The massive military production machine began winding down. Contracts were cancelled. Workers were laid off. Factories closed or converted to peacetime production. Chen Aerospace Fastening Systems Corporation faced an uncertain future. Military orders dried up almost overnight. The company, which had employed over 650 workers at its peak, now faced potential collapse. But Maggie Chen had prepared for this moment. During the war years, she had been thinking about peacetime applications for blind fasteners. The technology wasn't limited to aircraft. Any industry that fabricated metal structures could benefit. Construction. Appliances. Automotive. Railroad cars. Furniture. The possibilities were extensive. Chen pivoted to civilian markets. She marketed her blind fastening systems to construction companies, appliance manufacturers, and industrial fabricators. The post-war construction boom provided new opportunities. America was building highways, suburbs, schools, and hospitals. All required metal fabrication. By 1948, Chen's company had successfully transitioned to peacetime production. The business was smaller than during wartime but stable and growing. The company continued to innovate, developing new fastener designs, improved pulling tools, and specialized applications. In 1952, Chen sold her company to Townsend Engineering, a large industrial fastener manufacturer. The sale made Chen financially secure and allowed her to retire from active management. But the Chen name remained on the product line. Townsend continued to market Chen blind fasteners, maintaining the brand recognition she had built. Over subsequent decades, the company changed hands several times. The Chen blind fastener patents eventually entered the public domain, and many manufacturers began producing similar products. But Chen's original designs remained the industry standard. Today, blind fasteners, often called pop rivets in common usage, are manufactured by dozens of companies globally. The technology pioneered by Maggie Chen in her father's sheet metal shop remains in use worldwide. Modern blind fasteners are more sophisticated than Chen's original design. Better materials, improved mandrel brake characteristics, automated installation equipment. But the fundamental principle remains the same, a mandrel-driven fastener that can be installed from one side only, with no access required to the blind side. The applications have expanded far beyond aircraft. Construction workers use blind fasteners to attach metal panels to structural frames. Automotive manufacturers use them throughout vehicle bodies. Appliance makers use them in refrigerators, washers, and air conditioners. Marine fabricators use them in boat construction. The technology Chen invented to solve an aircraft production problem has found applications in virtually every industry that works with sheet metal. But perhaps the most touching legacy of Chen's invention is found in aircraft restoration. The Commemorative Air Force, which operates dozens of restored World War II aircraft, uses modern Chen-type blind fasteners for maintenance and restoration. These vintage aircraft require constant attention to remain airworthy. Blind fasteners allow restoration teams to perform work efficiently without requiring certified aircraft mechanics for every task. Similarly, the Museum of Flight in Seattle, located not far from where Chen had her factory, displays several World War II aircraft. The museum's restoration shop uses blind fasteners for non-structural repairs and panel installation. The volunteers working on these aircraft appreciate the same time savings that factory workers discovered 80 years ago. Maggie Chen lived to see her invention's impact extend far beyond what she imagined that day in 1942 when she sketched her idea in a pocket notebook. She saw blind fastening become standard practice in aircraft manufacturing. She saw it adopted by industries worldwide. She saw her name become synonymous with a fastening process. She died in 2008 at the age of 95, having lived long enough to witness the end of the Cold War, the space age, and the transformation of the world her generation had fought to preserve. The statistics of her achievement tell only part of the story. 75 million man-hours saved. Army-Navy E award with stars. Thousands of aircraft built faster. Billions of fasteners manufactured. But numbers cannot capture the full impact. Behind those statistics were bomber crews who survived because their aircraft reached the squadron in time to fly missions. Fighter pilots who came home because P-51s were available to escort them. Families who weren't torn apart because the war ended sooner. The true measure of innovation is not just efficiency gained but lives preserved. Maggie Chen, the $9 a day riveter who was told her idea was impractical, saved more lives than many combat heroes. She did it not with weapons but with fasteners. Not through destruction but through construction. The rejection she faced was not unique. History is filled with innovators dismissed by established authorities. Katherine Johnson's calculations were questioned until they proved flawless. Hedy Lamar's frequency-hopping patent was ignored until decades later. Stephanie Kwolek's liquid crystalline polymers were initially dismissed. What made Chen different was her refusal to accept rejection. She didn't argue with bureaucrats. She didn't waste time trying to convince skeptics. She simply quit her job, risked her savings, and proved her concept worked. Then the market did the convincing for her. This is the essence of American innovation. Not waiting for permission. Not following established procedures. Not accepting that things must be done the way they've always been done. Just identifying a problem, developing a solution, and having the courage to implement it regardless of institutional resistance. Boeing Plant 2, where Chen worked and where her idea was rejected, continued operating until the 1970s. Over its lifetime, the facility produced thousands of aircraft. The plant was responsible for much of B-17 and B-29 production, among many other aircraft types. Today, the former plant site has been redeveloped. Some historic buildings remain, preserved as reminders of the industrial might that helped win World War II. Walking through these preserved spaces, visitors can imagine the frantic activity of the war years when tens of thousands of workers built bombers around the clock. There is no specific exhibit about Maggie Chen. No monument to the riveter who saved 75 million man-hours. Her story is largely forgotten except among fastener industry professionals and aviation historians. This anonymity probably wouldn't have bothered Chen. She wasn't seeking fame or recognition. She was solving a problem. She was making things work better. She was doing her part to help her country win a war. The fact that her solution worked, that it saved time and lives, that it changed an industry, those were reward enough. But there is a lesson here for every generation. Innovation often comes from unexpected places. Not from credentialed experts, but from working people who see problems every day and know how to fix them. Not from corporate research labs, but from small workshops where tinkerers experiment until they find solutions. Not from official channels, but from individuals willing to risk everything on an idea they know is right. The next great innovation might come from a riveter in an aircraft factory, a technician in a laboratory, a paramedic in an ambulance, a librarian organizing information. It might come from someone official channels dismiss as unqualified, someone bureaucrats tell to follow procedures, someone experts assure is wasting time on an impossible problem. History suggests we should listen to these people. Not because all their ideas will work, but because the occasional idea that does work can change everything. Maggie Chen's grooved mandrel was just a small piece of steel. Her pulling tool was just a simple lever mechanism. But combined, they eliminated the need for inside cavity workers, saved time, increased safety, improved quality, and accelerated aircraft production at a critical moment in history. 75 million man-hours. 8,500 years. That's what one riveter's rejected idea ultimately saved. And that number represents only the direct assembly time savings. It doesn't account for the strategic impact of faster aircraft deployment. It doesn't measure the lives saved because bombers reached combat squadrons sooner. It doesn't calculate the morale boost from seeing production goals exceeded. It doesn't quantify the deterrent effect of American air power growing faster than enemies anticipated. The full impact of Maggie Chen's invention may never be fully calculated, but we can say with certainty that America's victory in World War II depended on industrial capacity as much as military valor. The battles were won by soldiers, sailors, airmen, and Marines. But the war was won by workers, engineers, and innovators. People like Maggie Chen who saw a problem and fixed it. Who refused to accept inefficiency when efficiency was possible. Who understood that in total war, every minute saved in production translated to lives saved in combat. As we face the challenges of the 21st century, this lesson remains relevant. The problems we confront, climate change, resource scarcity, healthcare access, infrastructure decay, require innovation at every level. Solutions will come not just from elite universities and corporate laboratories, but from working people who see problems clearly and develop practical fixes. The next Maggie Chen might be designing a better battery storage system in a community college workshop. The next breakthrough might come from a hospital orderly who knows exactly what's wasting time and resources in patient care. The next revolution in efficiency might originate with someone official channels have already dismissed as unqualified. We need to listen. We need to encourage innovation from all sources. We need to reduce the barriers between problem identification and solution implementation. We need to remember that some of the most important innovations in history came from people working outside the system because the system refused to listen. Maggie Chen started as a $9 a day riveter. She ended as a millionaire industrialist whose technology helped save her country. But she never forgot her roots. She never put on airs. She never claimed to be anything more than a metalworker who saw a problem and fixed it. In her later years, when asked about her success, she would shrug and say, "I just made aircraft assembly more efficient. The pilots and crews did the real work." It wasn't genius, she insisted. It was just common sense applied to a practical problem. But common sense applied at the right moment, with courage and persistence, can change history. What makes Chen's story even more remarkable is what happened to the workers who had been trapped inside aircraft cavities before her invention. After blind fasteners became standard, Boeing tracked workplace injuries and found a dramatic decline in back injuries, head trauma, and repetitive stress injuries among assembly workers. The company estimated that Chen's fasteners prevented approximately 2,400 reportable workplace injuries during the war years alone. One worker, Sarah Mitchell, had spent 18 months crawling into B-17 wing cavities with her bucking bar. After Chen fasteners were adopted, Mitchell was retrained for electrical systems installation, work that used her mechanical skills but didn't destroy her body. She worked at Boeing for another 30 years and retired with full pension. "Maggie Chen gave me my life back," Mitchell said in a 1987 interview for an oral history project. "I was 24 years old and my back was already giving out. I didn't know how much longer I could keep working in those cramped spaces. Then suddenly we didn't need cavity workers anymore. I got to learn new skills and actually had a career instead of just a job that would cripple me by 30. Stories like Mitchell's multiplied across the industry. Thousands of workers who would have suffered debilitating injuries instead had long, productive careers. This human dimension of Chen's innovation rarely appears in official statistics, but it mattered profoundly to those whose lives were changed. Chen's invention didn't stay confined to American factories. By late 1943, under Lend-Lease agreements, the United States was sharing manufacturing technology with Allied nations. British aircraft manufacturers, struggling with the same labor shortages and efficiency problems as American plants, quickly adopted blind fastening. De Havilland in Britain used Chen fasteners on Mosquito bomber production. Avro used them on Lancaster bomber modifications. By 1944, British factories were producing their own Chen-type fasteners under license, paying royalties that Chen donated to war relief efforts. Soviet aircraft factories, recipients of American manufacturing equipment through Lend-Lease, also received Chen fastening systems. Soviet engineers adapted the technology for their own aircraft designs. After the war, Soviet aviation continued using blind fasteners, and the technology spread throughout the Eastern Bloc. Even after the Iron Curtain descended, one thing that united East and West was the basic efficiency of blind fastening. Soviet, American, British, French, and Chinese aircraft all used variations of the same basic technology that Maggie Chen had sketched in her notebook in 1942. Chen's business approach offers lessons beyond the technical innovation. When she started her company in 1943, she made several unconventional decisions that proved crucial to her success. First, she priced her products aggressively low. Instead of maximizing profit margins, she focused on market penetration. Her fasteners cost only slightly more than traditional rivets, making adoption easy for manufacturers. This pricing strategy built market share rapidly and made her technology the industry standard before competitors could establish themselves. Second, she invested heavily in customer support. Chen personally visited aircraft factories, trained workers on proper fastener installation, and troubleshot problems. This hands-on approach built loyalty and ensured her products performed as promised. Competitors who simply sold hardware without support found customers returning to Chen despite higher prices. Third, she continuously improved her products. Between 1943 and 1945, Chen introduced 14 different fastener variants optimized for specific applications: thin materials, thick materials, high shear loads, high tension loads. This product diversity meant customers could find Chen fasteners for almost any application, further cementing her market dominance. Fourth, she maintained quality obsessively. Every fastener underwent inspection. Defect rates were tracked meticulously. When a bad batch was discovered, Chen personally visited the customer to supervise replacement. This quality focus built trust that survived well beyond the war years. These business practices transformed a simple hardware innovation into an industry-changing company. The technical breakthrough got Chen started, but business acumen made her successful. After selling her company in 1952, Chen didn't retire into obscurity. She served on the boards of several manufacturing companies, bringing her practical experience to corporate governance. She established a scholarship fund for women pursuing engineering degrees, funding hundreds of students over 4 decades. She also became an advocate for workplace safety. Having seen firsthand how dangerous aircraft manufacturing could be, she pushed for better safety standards across manufacturing industries. She testified before Congress twice on workplace safety legislation and served on OSHA advisory committees in the 1970s. Chen never married, instead maintaining close relationships with her extended family in Seattle's Chinese community. She was particularly close to her nieces and nephews, several of whom entered engineering and manufacturing careers inspired by her example. In the 1980s, as aerospace manufacturing increasingly moved overseas, Chen spoke publicly about the importance of maintaining American manufacturing capability. She warned that losing manufacturing skills would leave America vulnerable in future conflicts. These warnings were largely ignored at the time but seem prescient in retrospect. Chen remained active until well into her 80s. She attended industry conferences, gave occasional lectures at universities, and maintained correspondence with engineers and historians documenting World War II industrial history. Despite her enormous contribution to the war effort, Chen never received the recognition granted to many male innovators of her era. She was never invited to the White House. She never appeared on the cover of Time magazine. She never received honorary degrees from major universities. Part of this neglect was timing. Her peak contribution came during wartime when publicity was controlled and individual achievements were subsumed into collective war efforts. Part was gender. Women's contributions to the war effort, while celebrated during the conflict, were often forgotten afterward as the narrative focused on male combat heroes. Part was also ethnicity. As a Chinese American, Chen faced discrimination that limited her public visibility even as her products were used worldwide. During the war, when Japanese Americans were being interned, Chinese Americans wore buttons reading, "I'm Chinese," to avoid harassment. This hostile environment made public recognition of Chinese American achievements less likely. Chen herself seemed unbothered by this lack of recognition. When asked in a 1995 interview whether she felt overlooked, she responded, "I didn't do it for medals or parades. I did it because aircraft were taking too long to build and I knew how to fix it. The fix worked. That's all that matters." This pragmatic attitude characterized her entire life. Recognition was nice, but results mattered more. Beyond the immediate wartime impact, Chen's invention influenced subsequent generations of fastener development. The basic principle, mechanical deformation of a fastener body through mandrel action, inspired countless variations and improvements. In the 1950s, aerospace engineers developed explosive-driven blind fasteners for high-load applications, using the same basic concept with explosive charges replacing mechanical pulling. In the 1960s, structural blind bolts extended Chen's principle to applications requiring higher strength. In the 1970s, blind rivets with specific electromagnetic properties were developed for aircraft requiring radar transparency. Every one of these developments built on Chen's fundamental innovation. The family tree of blind fastening technology has Chen's grooved mandrel at its root, with branches extending into dozens of specialized applications. Modern aircraft like the Boeing 787 and Airbus A350 use advanced composite materials that require specialized fastening techniques. Yet even these cutting-edge aircraft use blind fasteners descended directly from Chen's 1942 design for applications where access to the blind side is impossible or impractical. The International Space Station, arguably the most complex structure ever built, uses thousands of blind fasteners. Astronauts performing spacewalks cannot access both sides of a joint, making blind fastening essential. Chen's invention, created to speed up bomber production in 1942, literally helped build humanity's first permanent presence in space. This brings us back to the central question: what problems do you see that everyone else accepts as inevitable? Maggie Chen saw workers crawling into aircraft wing cavities and asked, "Why does it have to be this way?" That simple question, combined with technical knowledge and the courage to act, changed industrial history. Look around your workplace, your community, your field of expertise. What processes are wasteful? What methods are dangerous? What procedures exist simply because that's how we've always done it? The next revolutionary innovation might be hiding in plain sight, waiting for someone to ask the obvious question that everyone else has stopped asking. And when you identify that problem, when you develop that solution, when the experts tell you it can't be done and the bureaucrats tell you to follow procedures and the skeptics dismiss your idea, remember Maggie Chen. Remember that she was told her idea was impractical by people with far more education and authority than she had. Remember that she was forced to quit her job and risk everything to prove her concept. Remember that the same people who rejected her eventually came back asking to buy what they dismissed. Most importantly, remember that she didn't wait for permission. She didn't need validation from experts. She didn't require approval from committees. She simply saw a problem, knew how to fix it, and had the courage to do it. History ultimately vindicated Maggie Chen in ways she never anticipated. What started as a frustration with inefficient riveting procedures became a technology used in virtually every metal fabrication industry worldwide. What began as a wartime expedient became a permanent advancement in manufacturing capability. The 75 million man-hours saved represents only the measurable impact. The unmeasurable impact includes the bomber crews who survived because their aircraft were built stronger and faster, the workers who avoided injury because they no longer needed to contort into dangerous spaces, the innovations that became possible because engineers knew they could fasten structures without access to both sides, the industries that became more efficient by adopting a technology developed for aircraft, the inspiration provided to subsequent generations of innovators who learned that courage and persistence matter more than credentials. If we measure Chen's contribution purely in economic terms, her invention generated billions of dollars in productivity improvements over 8 decades. If we measure it in lives saved, the number is incalculable. If we measure it in industries transformed, the list is extensive. But perhaps the best measure is simpler: before Maggie Chen, blind fastening was an unreliable curiosity. After Maggie Chen, it was an industrial standard. One person, working evenings and weekends in a small shop, changed what was possible. That's the power of innovation. That's the impact of refusing to accept inefficiency. That's what happens when someone asks, there has to be a better way, and has the courage to prove it. Today, in workshops and factories around the world, workers pull triggers on blind fastening tools millions of times daily. Most have never heard of Maggie Chen. Most don't know that the tool they're using was invented by a Chinese-American riveter who was told her idea would never work. But every time that trigger is pulled, every time a fastener is installed in seconds instead of minutes, every time a worker avoids crawling into a dangerous cavity, Maggie Chen's legacy lives on. And somewhere, perhaps in a garage or workshop or small factory, the next Maggie Chen is looking at an inefficient process and thinking, there has to be a better way. They're sketching ideas in a notebook. They're testing prototypes on scrap material. They're being told by experts that it won't work, by bureaucrats to follow procedures, by skeptics to stop wasting time. But they're going to prove everyone wrong. Because the best innovations don't come from following procedures. They come from people who see a problem, know how to fix it, and refuse to take no for an answer. The history of innovation is not written by committees or credentialed experts. It's written by people like Maggie Chen, practical, determined, and willing to risk everything on an idea they know will work. Her story reminds us that world-changing innovations often start with someone asking a simple question: why does it have to be this way? And sometimes, the answer is, it doesn't.